Hello. So welcome all to the World Quantum Day in our group, Theoretical Sciences group of NICER. I see some of you have joined. The rest I hope will join soon. I hope everyone is able to hear me.
Yes, sir. Yes.
Very good. Very good. So let us crack on. So my talk would be about what is quantum, which has attracted me to this field. First, a little bit about myself. I'm Colin Benjamin. I have been working in this field for the past 20 years or more. I did my PhD in Institute of Physics, and then I moved for my postdoctoral at Salerno in Italy, then as a CNRS postdoc at Marseille, France, then at Leeds, and then in University of Georgia in the US. And after that, I have been a faculty here in the School of Physical Sciences at NICER from 2011 onwards. So during this period, in our group, we have already finished 2 PhDs. Those 2 students, one of them will be speaking just after me, and another student is a postdoc. And there are another 3 students who are working with me as PhD students. There have been postdocs in our group before. And then we have master students who have worked. And some of the master students also will be speaking during this time. So hopefully you'll know what we work on, why we work on this, and what are the important things which are happening in this field currently. Okay, so let me move on. So the outline of my talk is as follows. I'll briefly describe this age we are living in. So this age which has started from the Industrial Revolution till now, the age of the quantum. How do we describe it? From where we have come and where we are going. And then specifically what we are doing in our group. So in quantum information, in quantum nanoscience, and then in quantum computation as well. Okay. So Industrial Revolution, we know, started with the invention of the steam engine. That was the big breakthrough that started man from a, I won't say primitive, from medieval times to the modern age. So that started the transition from the medieval to the modern. So the cheap energy that men found was energy in coal, and there was rapid mechanization of the textile industry. So which made processing and developing clothes, mining started in a big way. So that all made steel making, iron ore, and all of that. So that helped in transport. Mobility increased. Earlier, people used to rarely go across continents, apart from through ships. But then mobility inside countries increased drastically. So the train was the first innovation. And most of the big players during this time in this industrial revolution were the European countries. As time moved forward, the second industrial revolution, which is called, was the revolution in communication. So from the growth in transport to then the growth in communication via the telegraph, the telephone, then electric bulb. And we know this has all been pioneered by physicists, whether it's Maxwell or Faraday in electromagnetism. And here again, apart from Europe, America comes into the picture, where the second industrial revolution on communication was mainly led by America. And beyond the Europe and America, there are Asian powers which are making the presence felt, especially Japan, which came into the world stage with its own version of its industrial revolution, which really shook the European countries, till then which had a hegemony over technology. And of course, Einstein wrote his famous 5 papers, which again revolutionized physics. Then comes the age of science, or specifically the birth of the quantum revolution. And not only quantum revolution, which was pioneered by these people in the first Solvay conference we see with Einstein, Bohr, and others, we had the revolution in petrol that made mass transit through cars, aeroplanes, much more easier and possible. And then medicine antibiotics, penicillin, radio, television. So the further advancement in communication. And through quantum mechanics, we could have a piercing gaze into tiny structures like the DNA and others. So those all came into fruition during this time. And the most important players again were the European countries and America. After that, a big jump happened due to the Second World War, and that we came from the quantum revolution to the atomic of the nuclear age. So the atom bomb was dropped on Hiroshima and Nagasaki, and by the end of the war, the Soviet Union had also developed its atom bomb. Then China in 1964, and India in 1975, and then Pakistan in 1998, all developed nuclear weapons. And this age, which is still with us, the nuclear atomic age, was the beginning of science dominating everything. After that, after the nuclear age came into fruition, also came the space race. The space race was, and of course, before I go to space race, I have to say that this nuclear was the first occasion when there was a race between countries to develop nuclear weapons. In the other revolutions, there was no race because it was mainly led by the European countries, and if there was a race, it was confined to the continent of Europe and maybe America. But after this, the nuclear race was worldwide. So every country wanted its own nuclear bomb. And likewise, in the space race, we see first USSR and then USA competing with each other to gain an advantage in the space race. And of course, in these kinds of races, there is not always competition, there's always cooperation also. So we have the International Space Station, which is a joint effort from many countries, American, European, Russians, all countries are involved in the space station. And of course, in this field also, there's been major developments. For example, in China, they developed an anti-satellite missile in 2007. And of course, China also has made its presence felt in the space race. Then we come to the age now. The current age we are living in is the quantum age. And it started with a fantastic experiment by the Jian Wei Pan group, where they teleported a quantum signal from Earth to space. It's around 1400 kilometers, and they could do it, and they could show that. The earlier record was quantum teleportation about 143 kilometers, and that was on Earth, somewhere in Europe. They teleported a quantum signal from one part to another part. So these quantum signals were carried by photons, and therefore they could beat the decoherence, and therefore they could be transmitted over long ranges. And of course, it is not just restricted to quantum communication. Quantum computers came to fruition, and these are called noisy intermediate scale quantum computing. The first one was by IBM, the IBM 1 and on. Till now, IBM, the maximum number of qubits it has got working on its quantum computer is 53 qubits. And then there are private players, all are private players here, IBM, Google, Rigetti. Only China has a university, and it developed its own version of quantum computing with 76 qubits. And the main players now are US and China. These are the two powers which are competing to control the quantum race. And Europe and Russia are also major players, along with India and many other countries. But the major competition is now between US and China. What was the space race between US and Russia is now the quantum race is between US and China, who can develop better and better quantum computers, who can develop better and better technologies for quantum communication. And the thing is, if we develop more and more better communication or quantum computing abilities, it has also a major application in cryptography. So because most of our cryptography, that is the secret codes, the ciphers, are controlled by classical machinery, developing a quantum computer will help us beat those. So the country which has the advantage in the quantum computing race will again have an advantage over all other countries in learning about the secrets of what the other country doesn't want to be revealed. And therefore it will help it to control the politics and other things of that country. So therefore, this race, which is now really a so all or nothing race almost between US and China, is it's gaining traction, and everyone is enamored by it, and everyone has been entangled by it also. The surrounding countries are also in this race. So where are we in this quantum computing thing? So we have this noisy intermediate scale quantum. These are quantum computers which are built with 50 to 100 qubits, and these uh, have shown promise that they can perform tasks beyond the reach of classical computers. Now, why we call them intermediate? Because the range is 50 to 100 qubits. And they're noisy because there is still only imperfect control. We are not able to control very effectively the qubits. So the qubits can do something which is beyond us also. And therefore, there are error prone. So all quantum computers which have been developed are this type. And there is a significant difference between different platforms. The superconducting qubits have some advantages over the ion trap, and the ion trap have some advantages over the superconducting. But these are the two major platforms: superconducting qubits and ion trap qubits, through which one builds the quantum computer. Okay, so now I come to what works our field in this field we are interested in, and one of these is quantum games. So quantum games, this is a quantum version of the prisoner's dilemma, help us to develop strategies and schemes which are better or which can be compared against each other. So how a quantum strategy can beat a classical strategy? And what are strategies? Strategies are basically steps. Here we outline a few steps of the quantum prisoner's dilemma. So strategies are basically few steps which would help us to make a good algorithm. So the quantum games give us the ability to test one quantum algorithm against a classical, of one quantum algorithm against another quantum algorithm to check which one is better. And therefore, we are interested in these things. And of course, there is something about Vanning's criticism and all, which will be discussed by one of the students who will be speaking after me. And of course, we are also interested in quantum box. So this is on the left, you see a classical version of the random walk, which we know, which is pretty symmetric. And you toss a coin, either you go to the left and right, and you get a pretty good Gaussian distribution. And the standard deviation, that is the spread of the walker, goes as square root of the time steps. But a quantum walk is completely different. It is no longer Gaussian distribution, but it is depends upon what kind of initial state you take, and it spreads quadratically faster. So it spreads with t. So if I develop algorithms using quantum walks, they will be able to, especially search algorithms, they will be able to find out what I'm searching for quadratically faster than a classical algorithm would be able to. And in this context, we in our group have worked on some games, which are called parando games. The parando games are two losing games, which if you combine, can win. So in this context, we have shown that using quantum walkers, you can develop Parando's paradox, and you can check Parando's paradox, and also should play Parando games on quantum walkers. Not only you can play quantum games with, Parando games in the context of quantum walker. In case of a cyclic quantum walk, we can develop a version of the Parando game where we have two chaotic walkers which can be combined to make an ordered or periodic walk. So that also we have shown in our group. And the application is this. This has applications in quantum cryptography. Okay, so not only there are discrete time version of the quantum walk, there are also continuous time versions of the quantum walk. And here, instead of a coin or a shift operator, you have directly the unitary evolution of the whole Hamiltonian. So this Hamiltonian can be any system, two qubits interacting, or a graph, or whatever, quantum state in a graph, whatever, and you have to just evolve it in time and check the probability of finding the quantum state at some vertex. And depending upon these edges and all, and here also you'll get the standard deviation of the continuous time quantum walker goes as t. Most important thing in these quantum walks or quantum games, we have not taken into consideration the role of decoherence. So decoherence affects, as we saw in the NISQ type quantum computers, every quantum machine which are available. Now, how to take care of decoherence? One of the speakers after me will be speaking about that, is through coupling them to an environment, and that one can do through what is called the quantum stochastic walks. The next thing which we in our group do is on quantum thermodynamics and quantum thermoelectrics. We have two versions of quantum thermoelectrics. One is the steady state quantum heat engines, which again will be discussed later, and cyclic version, which are the quantum thermodynamic cycles. So steady state devices and cyclic heat engines like the Carnot and Otto engines, there are some differences. What are those differences? A steady state quantum heat engine converts heat to work without any macroscopic moving parts. That is, no time dependent parameter is involved, and the quantum thermoelectrics is controlled by the flow of microscopic particles such as electrons, phonons from one part of the system to another, and through this transport you do something, convert some heat to work. In the case of cyclic, you don't have transport, you have a closed system, not an open system which is interacting with the bath and the devices like in a steady state case, but you have a completely closed system where there is very limited or no interaction with the environment as such. And these are cyclic heat engines, the quantum version of those, the Carnot and Otto. And of course, cyclic heat engines revert to their initial position after the completion of the cycle. And of course, on the efficiency side, a cyclic heat engine is always better than a steady state device. Steady state devices can never outperform the Carnot efficiency, they're always limited by that. But the work that you generate can be greater in a steady state device than in a cyclic device. So if you want to know more about steady state heat engines, these are very nice physics reports on that. And there are some things about what is classical thermoelectrics versus quantum thermoelectrics, and that the techniques one uses to study classical thermoelectric engines are basically Boltzmann transport theory, while to understand quantum scattering, to understand quantum thermoelectrics, you need quantum scattering techniques by like the Landau-Boettcher transport theory, and one of the speakers after me will be elaborating on that. And this is a representative classical Otto cycle. It is a cyclic engine, and the work that is done in this cycle is the area in this curve here. I want to calculate the efficiency of those cyclic heat engines also. The difference between a classical and a quantum heat engine basically is the superposition which a quantum mechanical substance will have, which a classical substance won't have. Of course, there are two main things which differ a classical from a quantum, and that is superposition and entanglement. But here we don't work with entangled state, mainly the superposition state, which leads to discreteness of eigenenergies and quantum coherence in the dynamics of such cycles. Beyond quantum, we in our group also work on the Stackmaker game theory and many aspects of theoretical nanoscience, which I didn't talk about. One relates to quantum cyclic heat engines as well, using bilayer graphene also. We have worked on materials and different materials. And then in game theory also, this classical game theory we have worked on. So without any ado, I will now, so this is the schedule. After me is Subhajit. Subhajit is a senior project associate in our group. He just finished his PhD, and he will be talking about the ZBCP problem in Majorana detection. Thank you. So Subhajit, kindly share your screen.
Okay. You have to, it is written, I cannot share the screen.
Really? Why?
While the other participant is sharing. But you have to.
Okay. Let me stop. Why don't you switch on your video?
Interesting. Option is not there.
Yeah. So make it full screen and start.
My screen is visible.
Yeah.
Yeah. Okay. Good morning. So today I will talk about what is the ZVCP problem in myodana detection. So outlines of my talks are as follows. First, I will introduce to myodana bound states. Then I will discuss the recent controversy regarding the myodana bound states experiment of Leo Koven, where they claim to see that they find the signature of zero bias contents fix. I will also discuss the difference between trivial zero bias contents peak and topological zero bias contents peak, and also the motivation of our study. And also discuss little bit about our work, how to distinguish trivial zero bias conductance peak from topological zero bias conductance peak via local density of state and local magnetization density of states. And finally, I conclude. So first I will introduce what are myodana bound states. So myodana bound states are quasi-particle excitation inside the superconductors at zero energy, which are their own antiparticles. They are found at the boundary with a topological superconductor or topological insulator superconductor heterostructure, and also in nanowire superconductor hybrid devices. Myodana bound states have application in topological quantum computation. One of the popular signature of myodana bound state is the zero bias conductance peak with peak height 2 square by h. However, recently there is a controversy regarding this quantized peak height, quantized 2 square by h peak height. Recently in 2018, from Leo Koven's experimental group, they published a Nature paper where they claim that they report quantized conductance plateau with peak height 2 square by h in the zero bias conductance measurement in hybrid superconducting semiconducting nanowires, and which they interpret as the evidence for the presence of myodana bound states. But there are several inconsistencies which were pointed out by the other researchers like Frolov and Morkic and Maurik between the raw measurement data that was made available to them and the figures that were presented in their paper. Therefore, the Koven's group, they reanalyze all the data and they find that the new conductance calibration shifted the plateau values by 8% over the 2 square by h values, and which affected all of their results. Therefore they no longer claim to observe the quantized myodana conductance, and they retracted their paper and they provided a new manuscript with corrected and extended data sets, which is now available in archive, where they see the large zero bias peaks in INSB AL hybrid semiconducting superconducting nanostructures. Now, what is the main problem with zero bias conductance peak in case of myodana detection? The main problem is that many other papers have reported zero bias conductance peak due to the non-topology region. For example, anti-bound state induced by inhomogeneous chemical potential or quantum dose can also produce quantized ZBCP, and further disorder-induced random potential can also generate ZBCP with sufficient fine-tuning. Further, spin splitting, spin orbit coupling, or ordinary SOF superconductivity, they can generate a situation where trivial zero bias conductance peak is almost behave similarly like topological zero bias conductance peak. So the main question is how to distinguish this trivial zero bias conductance peak from topological zero bias conductance peak based on the current experimental techniques. So recently, to distinguish between trivial and topological zero bias conductance peak, some interferometric experiments were proposed. Further, there are some specific experimental tools through numerical simulation for different dialing conductance measurement to distinguish trivial myodana bound states and to distinguish topological myodana bound states and trivial anti-bound states. However, in our work, our main aim is to distinguish trivial zero bias conductance peak from topological zero bias conductance peak via local density of state and local magnetization density of states. So this is our system. We consider metal-metal superconductor junction where there is a spin fiber between two metallic regions, and the metal superconductor interface is modeled with a delta-like potential barrier. This is the Hamiltonian for spin fiber, where J0 is the exchange coupling between electron spin S and spin fiber spin S. This is the BTG Hamilton of our system. If we diagonalize the BTG Hamilton, we can get the wave functions in different regions of our system. And by using the interface boundary condition, we can get the different scattering amplitude for our systems. So we plot the charge conductance and as well as energy bound states in case of for trivial superconductor junction and also for topological superconductor junction. We find that for low values of exchange interaction and high values of spin prepares peak probability, a zero bias peak appear in the quantance vector, which is almost quantized at 2 square by h values. However, it arises due to the merger of two energy bound states. But
can I ask one question?
Yes.
You said you have calculated the charge conductance and the energy bound state. What about the spin conductance? Means you have calculated GC, right?
GC
you have only considered.
No, spin.
So you can also
no, via charge conductance we can see the signature of Majorana bound state. Spin conductance we did not calculate in this way.
Okay, means that's what I was asking. That is there any significance that you have not calculated, or like we can get any information from spin conductance?
No, for regarding Majorana bound state case, we do not get any information for from spin conductance.
Okay.
For topological superconductor junction, we see that zero bias quantized at 2 square by h values independent of all the junctions parameters. Further, also energy bound state is always marked as zero energy for all values of interface transparency Z. Also, we also plotted charge content as a function of interface transparency Z, and we see that for both trivial and topological superconductor junction, we see that it's for trivial superconductor junction in the tunneling regime charge content vanishes. However, for topological superconductor junction, charge content is constant at 2. Just a minute. Hello? हाँ 10:30 में। हाँ मैं तो बोला आपको। ठीक है, हाँ ठीक है, सॉरी So for we also plot zero energy charge conductance as a function of interface transparency Z. We see that for trivial superconductor junction, differential charge conductance vanishes in the tunneling limit. However, for topological superconductor junction, zero energy charge conductance is constant at 2 and it does not change with change of interface transparency Z. And also we find that for change of other parameters like spin or spin peak probability of spin people, the differential charge conductance remains constant at 2. Now, here we distinguish trivial zero bias quantity peak from topological zero bias quantity peak via local density of states. We plotted local density of states as a function of position x in both metallic and superconducting region for both trivial and topological superconducting junction. We find that for trivial superconductor junction, zero energy LUS shows a nice oscillation in the metallic region. However, for topological superconducting junction, zero energy LUS does not depend on the position x and it remains constant. And also for in the superconducting region, we find that the zero energy LUS show an exponential decay in the superconducting region. However, for topological superconducting junction, LUS shows an oscillator decay in the superconducting region. The region is in the metallic region. We find that the B1 on that is the normal phase coefficient is vanishes for topological superconducting junction due to the perfect anti-reflection. Therefore, zero energy LUS is constant. In the metallic,
we have just 1 or 2 minutes more.
Achha. It is constant for topological superconductor junction. However, for trivial superconductor junction, it is exponential. It is showing an oscillator decay due to this exponential factor.
I have one more question. You said there is perfect anti-reflection in this topological superconductor junction. So why are you getting this perfect anti-reflection for that?
The perfect anti-reflection for topological superconductor junction because there is a Majorana bound state form. Therefore, that the anti-reflection coefficient, normal reflection coefficients are all 0.
Means why this topological character is affecting this entrip reflection, like why it is making it perfect entrip reflection, like why this topological nature making it the perfect entrip reflection, why it is wrong?
It is a property for like metal topological superconducting junction.
Means for topological character means we can distinguish this topological superconductor from the trivial due to their topological character, like that due to few characters. So why that character means how that is affecting this entrip means perfect entrip reflection.
Means B1 means normal reflection coefficient all 0 for like pure superconductors, but here Majorana bounds will appear because the conductance will be
I think the question, sorry, the question is how it is being affected in such a way that why is the normal reflection is vanishes. Means what is it in the topological superconductor junction which makes the normal reflection vanish?
The total and reflection will be 1.
No. So that is the consequence. So I think the plausible answer is because of Majorana, unlike a Cooper pair, which is a pairing between two opposite spin, especially if it's a S wave, in case of Majorana, it is a superposition between an electron and a hole. And if a Majorana fermion exists at the junction, especially in a topological superconductor, we assume that a Majorana fermion exists. Therefore, in that context, electron will be perfectly reflected as if it doesn't see anything from that junction. So when you solve a simple BTK Hamiltonian problem with a P-wave superconductor, which has electron, a Cooper pair with 2 electrons having the same spin orientation, you will see that same thing. And when you solve that Burset-Kayayo paper, which has a P-wave, which is a P-wave superconductor with a Cooper pair. So P-wave superconductor Cooper pair differs from a S-wave superconductor Cooper pair. In this way, that in the P-wave case, there are 2 electrons have same spin orientation rather than opposite, like in a S-wave. So in that case, if you directly solve BTK, you will get this in spite of a Z barrier. Even if you have a tunneling barrier at the interface, you still get perfect entrip reflection.
Yes.
Okay. Thank you.
We also distinguish trivial.
I think we should end now.
Okay, so to conclude, we have shown a way to distinguish trivial ZBC from topological ZBC via LDS and LMDS. And we find that for low values of exchange coupling and high values of spin free spin, a zero bias coherence peak appears for trivial superconductor junction, which is almost similar to zero bias coherence peak for topological superconductor junction. To distinguish between them, we check the zero energy LDS and zero energy LMDS, and we find that for metallic region, zero energy LDS shows a periodic oscillation. However, for topological superconductor junction, it remains constant. And also in the superconducting region, zero energy LDS shows the exponential decay, but for topological superconductor junction, it shows an oscillator decay. Further, we also check the zero energy LM local magnetization density states, which shows a periodic oscillation in case of trivial superconductor junction, but for topological superconductor junction, it vanishes. But for in the superconducting region, in both cases, it shows an oscillator decay, but for topological superconductor junction, LMDS shows them superposition of 2 different type of periodic oscillations. So our results may be help experimentalists to distinguish trivial zero bias coherence peak from topological zero bias coherence peak via LDS and LMDS measurement. Thank you.
Okay, so thanks to Subhajit. The next speaker is Tushar. Tushadri has been working as a PhD student with me for the last 4.5 years, and she will be speaking on quantum short noise.
Can you see my screen?
Yeah, sure. So please switch on your video.
Okay. Okay, so I'm Tushadri Mapatra, and I'll be talking about quantum short noise and its uses. So first, I'll introduce that what is short noise, and then I'll explain this short noise cross correlation, which is also known as Henbury-Brown and twist correlations. Then how to use it in the megascopic system, in different system, I'll explain it. Then the motivation of our work, what is the problem, what work has been already done, and what are the problems they have been facing, and how using the short noise we can give an additional approach to solve that problem, like the proving this pairing symmetry by using this short noise cross correlation, and then I'll conclude. So short noise. Noise is a time-varying fluctuation in current, electric current, and the two major sources of current noise is thermal noise and short noise. So thermal noise is due to this temperature effect, which can't be avoided at finite temperature. But even at zero temperature, we found noise that is known as the short noise, which is due to the particle nature, or we can say discreteness of charge. So let's focus on first short noise. In the classical short noise and the quantum short noise. The classical short noise, this is the short noise due to the distance of the charged particles. We can say when there is no means it there is no effect of distinguishability or indistinguishable particles. But when it comes to this, then the quantum short noise comes to the picture and the Pauli exclusion principle. So here the S classical, this is 2ei. And so classical short noise is a simple way to measure the charge of the electron, of which Schottky gave this experiment using this vacuum tube. But when it comes to the quantum short noise, this Pauli exclusion principle comes to the picture, and this additional factor for this case, where 1 minus t, where t is the transmission probability, and this 1 minus t shows the reduction in the noise due to this Pauli exclusion principle. So I'll further explain that how we are using this for the different megascopic system. Next is the Henbury-Brown and twist effect. So actually Henbury-Brown and twist in 1956, they have measured this intensity correlations from the photon received from this star series, and they have found that this both the photons they have independently emitted photons are actually correlated. So they have found this correlation between both these photons emitted independently from the star. So they have introduced this intensity correlation, but it can be used for fermion and boson both. So for the single independent particle scattering, this short noise and the correlation is same for both boson and fermion. So this is the beam splitter, and 1 and 2 are the sources, and 3 and 4 are the detectors. So when one particle is coming from one of the source, it can end up in any of the detector. But when it comes to the more than one particle, this Pauli exclusion principle comes to the picture, and in fermion we can see the no bunching effect. When there is two particle, one will be end in each of the detector. But in case of boson, either both can end at 3 or both can end at the detector 4, and either one in each of the detector 3 and 4, and that is known as the bunching effect in the boson. So that is how this is different with this Henbury-Brown and twist correlation for fermion and boson. Next, I'll explain about the short noise in metal-metal junction. First, I'll start from this. So in the metal-metal junction, let's say normal metal left, right, normal metal are the right normal metal, and BL are the outgoing particles, and AL and AR are the incoming particles. So these are the function for both, and this current operator for both the lead IL. Here this I have explained for the IL. And average current also we can take it out for FL and FR are the Fermi function in left and right normal metal, which will be equal to the Heaviside theta function at zero temperature. So this is the average current, and then I'll explain the how to calculate the short noise in this metal-metal junction. The short noise is this current correlation between the contact alpha and beta. So alpha and beta are the both the contacts we can take as a left normal metal or right normal metal. So T and T prime is the time difference with the T. After Fourier transform, this will be this short noise power. And yes, here we are focusing on the zero frequency short noise, because when we are taking finite frequency, the frequency effect will come to the picture, and we can't get the exact information that we want to get from the short noise. It won't be the pure short noise. That is why we're focusing on the zero frequency short noise. So from this formula, we can calculate this short noise autocorrelation when both the contact will be same, and cross correlation when both the contact will be different. So this is the formula. And yes, for this differential short noise cross correlation for normal metal junction, we are getting the negative differential short noise cross correlation, and that is due to the fermionic effect. When we are calculating this for photon or a boson, we'll see the positive cross correlation, but here we are seeing this negative cross correlation. Next, the short noise in different mesoscopic system. First, I'll explain this in a metal superconductor junction and then metal superconductor metal hybrid junction. So in metal superconductor junction, we know that there's an Andreev reflection process comes to the picture when this electron incident from the left normal metal creating a Cooper pair and reflecting back as a whole. So where we are calculating this IL average current and the short noise auto correlation from the formula I have already given here, explained here. And this is the differential short noise, where A is the Andreev reflection probability, B is the normal reflection probability. And when it comes to this metal superconductor metal junction, two more processes comes to the picture, and that is important for the application in quantum computation, like topological quantum computation and many things. Like when electron from the left normal metal transmitted as electron to the right normal metal, this process is known as elastic cotunneling. And when the electron from the left normal metal goes as transmitted as whole to the right normal metal, it known as this cross Andreev reflection, or we can say that to the Cooper pair rupture or split, Cooper pair splitting to the means electron hole to the both the normal metals. So we can see that we get this entangled electron from this cross Andreev reflection, which will be helpful in the superconducting qubit and quantum computations. So this is the formula, generalized formula to find the short noise cross correlation when I and G are the contacts. Next, motivation for our work. Why it is important for our problem? What is the problem they have been facing? So the topological superconductors are known as this. They host the Majorana bound state, and that's why it is potentially important for this topological quantum computation. And the work previously done and the problem they have been facing is one of the important experiment is the night shift experiment, and they can distinguish the spin singlet and spin triplet pairing. I'll explain the pairing in the next slide. But they couldn't distinguish the topological character from the non-topological superconductors. And the theoretical approach in the previous work like CFI, they have been given. Now they can distinguish this chiral and helical p superconductor, but still they are unable to distinguish the gapful or the nodal or like topological character from the unconventional superconductors. So seeing all this problem, we have been trying to probe the different pairing symmetry using short noise cross correlations. So in the next slide, first I'll explain that what is the pairing symmetry. So the total wave function of a Cooper pair, as the Cooper pair consists of two electrons known as the composite boson, and the total wave function is anti-symmetry. So when the spin singlet, if for this S0, the orbital part will be even parity, and for the spin triplet, when this S is 1, the orbital part will be odd parity. So for the spin singlet S0, the even parity L can be 0 or 2 for the S wave and D wave, and for the spin triplet, when S is 1, the odd parity will be L equal to 1 for P wave and L equal to 3 equal to F wave. Then I will show you how this S
you have
D
just
wave.
1 or 2 minutes more.
Okay. So here this is one of the representation to see this Fermi on the Fermi surface is pairing potential, like how this vanishes, like how this is nodal and gapful. But Px, Py, and these two, we can see these are the nodal. And the nodes are found along this y-axis and x-axis. And here it is along this diagonal of xy and along the x-axis. But chiral P and chiral D are gapful in 2D unconventional superconductor. So another means this is our like whole, we can conclude this all the pairing symmetries like this. First the non-topological and topological, then based on whether the nodes are present or not, and then this triplet pairing due to the spin components. From the spin component, it can be explained, the pairing potential can be explained with the D vector, and for the singlets, it can explain with the psi scalar term. And one other way to also get differentiate the topological and non-topological character is from the normalized conductance versus this barrier standard zero bias, where you can see the quantized value for topological and non-quantized value for this non-topological superconductors, which comes in line with the tenfold symmetry class, where we can distinguish all the topological and non-topological superconductors. Then this is our setup. This is the pairing potential for spin triplet and spin singlet pairing, and D vector and psi k scalar term I have already explained in the table. And for the non-local differential conductance, GK is the cross-centric conductance and the elastic quaternion conductance, and small d and small c are this reflection amplitude at for the cross-centric reflection and for the elastic quaternion. So here you can see that still we can distinguish this helical and chiral, but it is still difficult to distinguish other pairing symmetry. That's why we move to the short noise cross correlation, differential short noise cross correlation. This is the formula I've already explained, and we have chosen two setups: symmetric setup and non-local setup, and for different bias voltages. So here we can see this. You can clearly distinguish helical P along with this chiral and other pairing symmetries. Here also we can distinguish different pairing symmetries. Then we have moved to the short noise cross correlation. So in the short noise cross correlation, it is more visible that how we can clearly distinguish the different pairing symmetries. The red ones are the chiral, the blue is the helical, and the black one are the DXY and DXY means nodal singlet pairing symmetries. So from this, for the transparent barrier and tunnel barrier, we can clearly see the different pairings. We can distinguish the different pairing symmetries, and by tuning the bias voltages, we can clearly tune this cross correlations. So here this positive cross correlation mostly the signature of this Cooper pair splitting. So with this different processes, how this cross-centric reflection or elastic core tunneling contributing to the short noise cross correlation, and with this tuning of the bias voltage, we can easily control this Cooper pair splitting, and or we can say the presence of the entangled electrons. Then I'll conclude that in this non-local HBT correlation, that can be helpful to distinguish the gapful chiral, gapful helical, as well as the nodal superconductor, and from the all the topological pairing from the non-topological pairing. And the ZBCP that can distinguish the pairing symmetry with the different D direction, like this PX, PY, and PZ. But PXZ is this non-topological pairing symmetry, whereas PXX and PXY are topological. So this ZBCP can distinguish that thing. But in the short noise, using the short noise cross correlation, we can distinguish with this means all the pairing symmetry even with the different D direction. Thank you.
Okay, thank you.
Any question?
Yeah, no, we don't have time for more questions. But if there is if anyone wants to ask a question, please do now. The next speaker is Nani. Nani has been working with me for the past 2 years, first for the 6th semester project and now master's project, and she'll be speaking on quantum stochastic walks. And I would request everyone to please put their videos on. Thank you.
Good morning, everyone. Today I'll present a talk on some of my current work and a little bit of a glimpse in what I did in the past in my 6th semester project. The topic of my master's thesis is on some applications of quantum stochastic walks. From the topic, you must be thinking, what are quantum stochastic walks and why do we need them? Basically, quantum stochastic walks are a hybrid of classical random walks and quantum walks. And quantum stochastic walks can interpolate between classical random walks and quantum walks using a single parameter omega. And it uses the master equation with the density matrix as the main point. This is the master equation. Now, why do we need quantum stochastic walks? So what happens is in open quantum systems where interaction of the system is happening with the environment, the interaction is incoherent, which means that quantum walks cannot be used to model the system dynamics on those systems. In order to model interaction open systems which interact incoherently with the environment, we use quantum stochastic walks. In other words, quantum walks cannot be implemented on directed graphs, since their evolution is supposed to be unitary and phase coherent, which is why we use quantum stochastic walks, because they are a hybrid of classical random walks and quantum walks. So they can use the coherent part from the quantum box, and they can use the incoherent part from the classical random box. Quantum stochastic box can be monitored using a single parameter omega. So from the density matrix equation, this master equation, you can see the first term depicts the coherent part of the evolution that is taken from the quantum box, and the second term is taken from the incoherent part of the evolution, which is using the classical random box. Here, rho is just the density matrix, h is the Hamiltonian, and omega is the parameter which is used to interpolate classical random box and quantum box. And L are just the Lindblad operators. Now we use quantum stochastic box to study two problems. The first is we study exciton transport in the photosynthetic Fena-Matthews-Olsen complex. Second is we study ranking of web pages in the Google page rank algorithm. We use three schemes in order to do this. The first scheme is the pure dephasing scheme. In this case, what happens is the Lindblad operators, which are showed in the master equation, they depend only on the diagonal elements of the Hamiltonian. Whereas for the only incoherence transport scheme, what happens is the Lindblad operators depend on only the off-diagonal elements of the Hamiltonian, and for the dephasing with incoherence transport scheme, Lindblad operators take into account both the diagonal as well as off-diagonal elements. And these three schemes are just the different ways to exhibit the environmental effects on quantum systems. Now, I said that we're going to study exciton transport in the Fena-Matthews-Olsen complex. Now, what exactly is the Fena-Matthews-Olsen complex? This is known to be a light harvesting complex, which is present in green sulfur bacteria. So, it is used to do photosynthesis. This figure is just the real figure of the Fena-Matthews-Olsen complex. The green stuff is just this bacteriochlorophyll molecule, which has the chromophore sites. Now, why are we studying exciton transport in the Fena-Matthews-Olsen complex? Firstly, we are trying to find out the presence of entanglement in FMO complex. Secondly, we know that photosynthesis is supposed to be nearly 100% efficient process. Now, what is happening is many people have wondered where some quantum mechanics is involved in order to help the photosynthesis in showing this efficiency. So we try to detect the presence of a quantum speedup during exciton transport. So these are the two objectives that we are going to study in this exciton transport. Now what we've done is we have modeled the FMO complex as a graph where the vertices 1 to 7 just show the chromophoric sites, which are the bacteriochlorophyll molecules. And in order to model the interaction with the environment, we introduce a new vertex, which is the sync vertex, vertex number 8. And we make a directed edge from the vertex number 3 to vertex number 8, where vertex number 3 is the reaction center where the energy is stored and photosynthesis happens. The photon is captured at vertex number 6. And vertex number 8 is the newly introduced sync vertex, which is introduced by us. And this is a directed edge, which is used to indicate the incoherent interactions. Now, we have observed quantum speedup for pure dephasing scheme. So these figures are, this is the figure which, so we compute a bunch of observable, but most importantly, we compute the global entanglement and the localization time. So what happens is speedup is observed when the exciton stays in the super diffusive region for a longer time at a higher temperature as compared to a lower temperature. So in these figures, the black line represents omega is equal to 0.19, which is a temperature of approximately 77 Kelvin. And the red line, dashed line, represents omega is equal to 0.45, which is a temperature of around 300 Kelvin, which is life sustaining temperature at which the photosynthesis happens. So what we see, so figure A is for pure dephasing scheme, B is for only incoherent scattering scheme, C is for dephasing with incoherent scattering scheme. So from these figures, from figure A, you can see that the red line crosses the y is equal to 1 at a later time as compared to the black line, which is not the case for the other two. which means that for 300 Kelvin, which is omega equal to 0.45, the exciton stays at the super diffusive region for a longer period of time. Super diffusive region is just the region above the y equal to 1, and the region below y equal to 1 is subdiffusive region. So we observe a quantum speed up for the pure diffusing scheme.
You have 1 or 2 minutes more.
Secondly, we compute the global entanglement, and we see that for pure diffusing scheme, the global entanglement is the highest. So why are we doing all this? So first of all, we are trying to understand the reason behind the nearly 100% efficiency of excited transport. We are trying to find whether quantum mechanics is involved or not. Secondly, we are trying to find out if the entanglement is present in the complex, which this opens up many possibilities, because one of them is entanglement enhanced measurements. Secondly, now we come to the second problem that we're studying, which is the Google PageRank algorithm. What Google PageRank algorithm does is it puts those web pages which are most relevant to the nature of the search, and it uses the PageRank algorithm. So what PageRank algorithm does is it, so let's say we have a graph. So if you can see the figure, the vertex B, it has a higher rank because it has more number of links from other vertices. So which gives the vertex B a higher rank. But just the more number of links is not the only thing that accounts for ranking the web pages. The quality also matters. So you can see the vertex C also has a higher rank, but it does not have links from any of the other vertices, only one from vertex B. So because the rank of vertex B is high, and it has a link, and the vertex C has a link from vertex B, this in turn gives a higher rank to vertex C as well. This is what I mean when I say that quality of the links matters as well, not just the number of links is important. Now we study ranking in some networks using quantum stochastic walks. We use quantum PageRank algorithm, which uses the quantum stochastic walk master equation that I showed in the beginning. This is the figure that we are going to study. We rank the web pages in this particular figure. We have done more complex networks as well, but for now we're restricting it to this particular 8 vertex figure. We have plotted the page ranking versus the vertices. A is for pure dephasing, B is for only incoherence, and C is for dephasing with incoherence. Now what we see is in the pure dephasing scheme, we managed to resolve degeneracy between any of the vertices. None of the vertices have the same ranks, whereas for only incoherence and dephasing with incoherence, there are 2 vertices who have the same rank. Now, so from this we know that for pure dephasing scheme we have a richer Google search quality. So this was all that I did in my master's work. I'll just introduce a little bit in what I did in my past. What I did is I employed quantum strategies and entanglement in order to reduce congestion in quantum Pico networks. This is the figure for the quantum Pico networks. The applications for this work range from, so since I managed to reduce the congestion, this results in easier transfer of information. This results in easier transfer of information, and since I've used quantum strategies and since I've used entanglement, this also results in, there is also the possibility of more secure transfer of information using the quantum key distribution principle. That is all from my side, and I hope you enjoyed my talk.
Thank you so much. So next is Jabir. He will be speaking on Nash equilibrium and quantum gates. Jabir, would you please switch on your video?
Okay, hello, am I audible?
Yeah, you are audible.
Yeah, okay, sorry,
switch your video.
Yeah, my laptop camera is not working.
Oh, okay.
Yeah, okay. So is my presentation visible?
Yes.
Yeah, okay, so just start. Okay, so I'm going to talk about Nash equilibrium and quantum games. So this is an overview of my talk. So first I'll go through what is a game and 2 classic examples of a game, Prisoner's Dilemma and Hoctave game. Then I will talk about the quantum version of these games, and through which I will address the advantages of quantum games or quantum strategies over its classical counterpart. And so what is a game? So any interaction between multiple agents. So these agents can be people or organisms or even computer programs, in which each agent's payoff is affected by the decision made by other agents. So you can call these agents as players. So a simple mathematical definition of a simple game is as follows, where we have a set of players and a strategy set to each players, and the utility functions, which is mapping from the strategy profile to a real number. So as we can see, the utility function of a player is not only dependent on what strategy he chooses, it depends upon other players' strategies. So now we'll talk about what's Nash equilibrium and Pareto optimal. So Nash equilibrium is a recurrent outcome of a game. It's a strategy profile from which no player has an profitable deviation, or if he deviates from this particular strategy, he'll always get a lower payoff. So this is a mathematical definition of a Nash equilibrium. And Pareto optimal is a concept, is a solution concept in which an outcome is a Pareto optimal if no other outcome can help some players without any adversely affecting others. So we'll talk about this concept through an example, the classic example of Prisoner's Dilemma. So this is a payoff table of this game. So the strategies are cooperate and defect for both players, and these numbers represent a payoff, and these payoffs are follows. 0 means lifetime imprisonment, 1 means 10 imprisonment, 3 means 2 year imprisonment, and 5 means go free. So as we can see, the Nash equilibrium of this game is defect. It's because if players deviates from this Nash equilibrium to another strategy, which is cooperate, he will have to serve a lifetime imprisonment. And the Pareto optimal of this game is cooperate. And as you can see, this is the best outcome for all players. And if one player chooses to deviate, he might increase his payoff, but he decreases the other player's payoff substantially. Now we come to another classic example, which is the hawk-dove game. So hawks are generally very aggressive in nature, so they fight to take possession of resources, and doves are very calm and they don't fight. And so if hawk and hawk interact, we know the outcome will be a substantial loss. And hawk and dove interact. Dove is more calm, it won't engage in fight, and hawk can exploit all the resources. And if dove and dove interact, they are more patient, so they have a middle level payoff. So the Nash equilibrium of this game is hawk dove and dove hawk, as you can see. And the Pareto optimal is DD, dove. Okay, so since there is two asymmetric Nash equilibrium for this game, there will be a mixed strategy Nash equilibrium. And what are the applications of game theory in real life? Game theory is a very wide concept which is having a wide range of application in many fields, from economics to finance to physical sciences, and it goes on. And one classic example is vaccination. We can model a vaccination game, and in particular scenario, we get a payoff structure which is similar to this payoff structure of hawk-dove game, where the dove means vaccinate and hawk means do not vaccinate. And yeah. And now mixed strategy Nash equilibrium. So mixed strategy means a probability distribution of pair strategies. So if Alice plays with hawk with probability P and dove with 1 minus P, and Bob is playing Q and 1 minus Q. So that's a pure strategy. So pure strategy Nash equilibrium can be calculated as P and Q as 7 by 2, 7 by 2. So if we denote a pure strategy, mixed strategy as MCD, and we expand the payoff table, we get the following payoff table, and you can see how MCD is also a Nash equilibrium. So that's it. Now we'll come to the quantum version of this game. So the quantization of games was first done by D. Mayer, in which he quantized the classical penny flip game, non-zero sum penny flip game. So this work by Jens Eisert, M. Wilkins, and so you can call this work work is like for shorthand they call it as EWL paper. So in this work they quantize a non-zero sum game like Prisoner's Dilemma. So what they do is the protocol is that they assign the cooperate state and a defect state to the orthonormal basis of a qubit, which is get 0 and get 1. And so each player is assigned one qubit, and on which they locally apply a unitary operator. So a strategy of this game is this unitary operator. So this is a 2-parameter unitary operator which they use in their work, but this can be extended to 3-parameter or 4 parameters. So the strategy space is constrained in this way. So a cooperate operator is the identity operator, and defect operator will be the bit flip operator. And now the scheme is that the initial state of the game is entangled. So with using this entanglement operator, and gamma is entanglement parameters, which says the degree of entanglement, and we get the following state. And then finally, after players locally apply the unitary strategies, the state is finally entangled before measurement. So this is a quantum circuit diagram for this game. So this qubit is assigned to Alice, and this qubit is assigned to Bob. Then the state is entangled. Then players locally apply the unitary strategies and disentangle and do the measurement. And the expected payoff is can be calculated as follows. Now, this is a result of their paper, the EWL paper. So they parameterize these quantum strategies like so, and they get the for gamma is equal to 0, which means there is no entanglement, they get the following outcome, which is a separable distribution. But when gamma is equal to pi by 2, we get a very unique outcome. And for a particular strategy Q, which is defined as follows, we get a very unique payoff, in which the new Nash equilibrium of this quantum game will be QQ. And as you can see, you can clearly see the advantage of quantum strategies over classical the classical counterpart. So in the classical game, the Nash equilibrium was DD, which has obviously very lesser payoff than the Nash equilibrium in this version, this version of quantum resonance dilemma. Okay, so now since this paper was since this paper was published in 1999, there has been a lot of criticisms, comments, and debates on this scheme. So one of the early criticism is made by Van and Pike. So they argues that quantum games has nothing to offer more than classical games, because the strategies that quantum games produce are already present in classical games. For instance, the outcome CQ is same as the outcome DD, and QQ is same as CC, and so on. So this is one argument of their paper, and there are other arguments too. So in our recent work on is the essence of quantum games captured completely in an original classical game, we contest this argument with a simple quantum Hawkdorf game, in which the game produces outcomes which are not otherwise possible in the classical counterpart, and which is also more better outcomes. So this is a scheme for a quantum Hawkdorf game. We assign get 0 as Dove and get 1 as Hawk, and the bit flip operator as Hawk strategy, and the identity operator as Dove strategy. And when players apply, so the game is initially entangled. So the state of this quantum state is represented as the density metric state. So it's mainly because
you have 2 minutes.
Yeah. Okay. So this is a scheme, and now pure okay. So these are the pure strategies. So we consider a special case where players are only allowed to use quantum strategies, Q and M. M is a miracle move. It is just defined in the EWL paper, and in which they show the advantage of quantum player over a classically constrained player. And so this is the payoff outcome. And the Nash equilibrium you can see is QQ. And now we show with the random mix strategy how we can get a unique outcome of a game. So a random mix strategy, when these players apply these unitary strategies with a probability P and the other player with probability Q, we'll get this ensemble of quantum state, which is a mixed density metric state. So we can similarly calculate the expected payoff with this formula. And now we use a random mix strategy of Q and M, in which the players play Q with probability P and M is probability 1/2 and 1/2. So when we extend this, the prior pair of metrics to this random mix strategies, we get this following outcome. And you can see the outcome is really unique. And the RQM, the Nash equilibrium is still QQ, but the RQM outcome gives a new Pareto optimal, which has higher payoff than the Pareto, slightly higher payoff than the higher Pareto optimal of the classical counterpart, the classical outcome game, which is 15-15. So this is how we negate the Van Eyck-Spice association, and that quantum games has nothing to offer more than classical games. So that's it. So that's all.
Thank you, Jabir. Are there any questions?
Any question?
Okay. So we'll go to the next speaker on quantum thermoelectrics. It's Ritesh Das. Ritesh worked with me in his 6th semester project, and he's continuing, and we are writing a paper on this. So Ritesh, share your screen.
Yes, I'll share. So, hello.
Hi, continue.
So I hope I'm visible. Screen is visible.
Yeah.
Okay. So welcome to my talk on quantum thermoelectrics. So I'm Ritesh Das, part of the theoretical sciences lab at NICE. And I've been working on quantum thermoelectrics for more than a year now with Dr. Benjamin and his group. So what is thermoelectrics? Let's start with that. So thermoelectrics captures the study of conversion of charge current into heat current or vice versa. We can convert charge current to heat current or heat current to charge current. So why is this important? So this provides us a way to convert waste energy. For example, in cars, we have a lot of waste energy in combustion engines, which are cyclic engines, and they release like around 60 to 70% of the heat generated is wasted. So through thermoelectric devices, we can provide a conduit for that heat to be converted into, say, useful electrical energy. Like some cars have begun using that energy to power the radios and dashboards. Similarly, we can convert heat to energy directly. For example, there are now watches that work with body heat. And another purpose is to convert or to dissipate the heat generated in computers. For example, CPUs and GPUs, we have this problem of very high heat dissipation. This heats up the devices, and this in turn hampers performance. So in that, we use these kind of thermoelectrics that dissipate the heat generated. And of course, quantum computers, which also require thermoelectrics to function properly. And as Dr. Benjamin mentioned earlier, we have, after the arms race and space race, we are now in a quantum race. And while the Cold War may be over, espionage is still a big factor in the world stage, and anyone who controls quantum computers will have a major upper hand. So why do we study thermoelectric effects? So as expected, as I said before, there is a lot of energy wastage in the engines and devices that we currently have. For example, as we will see here in this figure, that the CPU's frequency goes down very rapidly when we have a very high temperature. And laptop users will identify with this problem, that there is a lot of heat generation in smaller devices. So to convert this heat into work or to dissipate this heat safely, we use thermoelectric devices. So this is just an overview of the thermoelectric effects, mainly the Seebeck effect and the Peltier effect. Seebeck effect is used to convert heat into charge current. And the Peltier effect does the opposite. It converts the charge into heat currents. So let's see what's happening here. So we have an N-doped semiconductor and a P-doped material. And we have a heat source and a cool source, cool side. So this heat diffuses the charge carriers to the other side. So here we see a negative potential develop and a positive here. Then a negative potential here and a positive potential here. So just through temperature, we are now able to drive a current in this system. Similarly, by driving a current, we can also cause the diffusion of heat from one side to other. So we can drive heat from one surface and dissipate it safely to another surface by driving a current. This helps us keep our devices safe or to convert the wastage heat generated into useful work. So now let's come to why we go into quantum thermoelectrics. What's the benefit of using quantum over classical? So as we know, so normally the charge and heat transport in materials with electrons or other fermions, they follow something called the Wiedemann-Franz law, where we know that the thermal conductance is equal to the proportional to the electrical conductance. But if we need a good thermoelectric, we need a low electrical conductance and a high thermal conductance. So for that, we need something called broken symmetry in the system. For example, we can break the electron hole symmetry or the time reversal symmetries in the system that allow us to get huge amounts of Seebeck coefficients, relatively good amounts of Seebeck coefficient, which helps us in designing better thermoelectrics. And another purpose is, as there is now a high demand for smaller technology, we need smaller components. And as the size of the components keeps going down, the quantum mechanics involved becomes more and more prevalent in these structures. And of course, in quantum thermoelectric devices, in small scale ones, we can manipulate charge and heat transport to in such a way, we can break symmetry in such a way that we get a high thermal power. And in our work, or in my work, basically, we focus on steady state engines. So these engines may not be as efficient as cyclic heat engines that will be explained later. They are much more reliable because they do not have any moving macroscopic parts. So there is less risk of them breaking. Further, they may not have a very high efficiency that can be comparable to cyclic heat engines. They, however, can have a good steady output power, which is good for having with a high efficiency. So our work focuses on thermoelectric transport in mesoscopic systems. So what is this? So mesoscopic is the link or the bridge between what is microscopic and what is macroscopic. So macroscopic will be whatever is greater than a millimeter or so. Microscopic goes to what is less than 10 nanometers or even less. So mesoscopic is the bridge between that area. So in microscopic, we have all molecules and atoms. In macroscopic, we go to bulk systems or we have biological cells. So in mesoscopic systems, we have things like topological insulators or topological systems that can have good thermoelectric values or other purposes as explained before. So to study the transport in mesoscopic systems, so in this quantum regime, we follow what is called the Landau vertical transport regime or the scattering system. So the scattering is focused or depends on the transmission probability, this T bar. So how scattering can work is there can be a scatterer and electrons and holes can go into the scatterer. Now they can either pass or they can be reflected, or in some cases like Marana bound states, they can go and stay and kick out another particle. So in this way, we have a probability of transmission of a particle. So using that transmission probability, we can relate the charge currents, the charge and heat currents IC and IQ with the thermodynamic forces of voltage and temperature gradient. So this is the matrix that relates them. It's nothing but just describes how many particles, what amount of charge of heat is carried through. And using these quantities, we can define useful quantities like the Seebeck coefficient, the Peltier coefficient that I showed earlier. And we can also find the maximum powers when functioning as a heat engine, or the cooling power and coefficient of performance, these quantities. Now we will look at how we can tune thermoelectric devices to perform better, to get a good transmission power that will help us in getting a good thermal power or efficiency. So straining is one such example, as done by Arjun and Dr. mentioned earlier. So in this work, they took a graphene layer and they strained it. So basically, they gave the material some dislocations, and using those dislocations as a parameter, they were able to show that we can get very high efficiencies and powers when we use this layer as a thermoelectric heat engine or a refrigerator. So we see that there is a good maximum power and a good efficiency at the maximum power as well, along with what is the coefficient of performance or the efficiency when the thermoelectric is performing as a refrigerator, and the cooling power at that. So another interesting thing that we see is that when we have a high efficiency, we start compromising power. So a part of the work is focused around finding the perfect compromise between the two, so we can have a good efficiency and a good power. So straining may not be the only, it's not the only way to tune these systems. We can also use Arnold boom flux, which is a magnetic field that passes through the thermoelectric. So in this system, we've shown a topological insulator. And also, as the Majorana fermions, the Majorana bound state discussed earlier, they can also be used to tamper with the thermoelectric performance, or we can also use the thermoelectric quantities or the coefficients as a parameter to detect Majorana states. And currently, we are working on those to detect Majorana bound states via these thermoelectric coefficients, and to study the effect of Majorana fermions on the thermoelectric coefficients as well. So that, yeah, the conclusion that the thermoelectric effects enable in the construction of these useful devices like heat engines, refrigerators, and conduits, and steady-state thermoelectrics are reliable and efficient alternative, or rather better alternative in some cases. And we can tune these devices for a high performance, and we can also use these to study other phenomena like the occurrence of Majorana bound states. So with that, I end my talk. So if there are any questions.
Thanks, Ritesh. If there are any questions from anyone, please go forward. Ritesh has stuck to time. That's very good. Okay, so we'll go to the last speaker, Aditya Prakash. He and I are working on a paper together now on quantum thermodynamic cycles. So Aditya, start.
Hi, so is my screen visible and I'm audible, right?
Yeah.
Yeah, so welcome to World Quantum Day. So I'm Aditya Prakash from NICER, School of Physical Sciences. So I'll talk on quantum thermodynamic cycles. Why quantum? Classical thermodynamics was doing so well, so why do we need quantum? According to Einstein, it is the only physical theory which he's sure it would be never overthrown. So what is the motivation for us to study quantum thermodynamics? So classical thermodynamics works well only for systems with large degrees of freedom. But when we scale down our system to say single particles or just few particles, we need a quantum theory to justify that. And thus we use quantum thermodynamics. And as Ritesh said, there is a need for smaller components. So quantum thermodynamics can help us in miniaturizing the technology. And under some conditions, researchers have also come up with papers showing that quantum heat cycles can surpass the maximum limit on the amount of work done by the classical thermodynamic cycles. So let's start with the basics of quantum thermodynamic cycles. So how is it different from a classical thermodynamic cycle? So in classical thermodynamic cycle, we have a classical working model, a gas, piston, etc. So in quantum thermodynamic cycle, we have a quantum working model, a quantum particle such as harmonic oscillator or infinite square well, etc. So here there's a Hamiltonian with energy eigenvalues En and the energy eigenstate as ket n. So we define the internal energy of the system as the expectation value of the Hamiltonian given by summation En Pn. So the differential equation would be du equal to summation En dPn plus Pn Den. So now if we compare this equation to our analog to first law, that is du is equal to dq plus dw. So we may identify that work is defined by the product of force times the change in the generalized coordinates. So here in quantum thermodynamics, the change in generalized coordinates corresponds to the change in eigenvalues. Hence, we identify dw as summation Pn Den, that is the occupation probability times the change in the energy eigenvalues. Similarly, we have dq is equal to summation En dPn, that is the heat exchanged by the system is equal to summation of energy eigenvalues with a product of change in the occupation probabilities of the system. So with these equations, if we move forward to define quantum thermodynamic processes, we have first is our quantum isothermal process. So in quantum isothermal process, the working substance is in kept contact with the heat bath and at constant temperature. So the energy gaps and the occupation probabilities of the system change such that the system remains in equilibrium with the heat bath throughout the process. So the only invariant quantity would be the temperature of the system. So for a simple case, if we take a two-level system with states say G and E, that is a ground state and excited state, and if it follows the Boltzmann distribution, so we can have the ratio of Pg by Pe of, that is the occupation probabilities, as E power beta Ei minus Eg, where beta is our 1 by Kt. So if the process if throughout the process this expression is followed between the two states and the temperature has been kept constant, so we may say that it's a quantum isothermal process. Yeah. So our next process is quantum isochoric process. So classically we know that isochoric processes are those where the work done or the work done on the system is zero. So as I defined earlier in my slide, dw is given by Pn Den. So in order to dw to be zero, we must have Den should be zero. That is, the energy eigenvalues of the system should remain constant. So to keep En constant, the occupation probabilities Pn and thus the entropy. Yes, so the entropy is related to occupation probability as S equal to minus Kb summation P ln P. So yeah, so the occupation probability and the entropy change such that the system the energy eigenvalues of the system remains constant until the working substance finally reaches the thermal equilibrium with the heat bath. So next we have quantum adiabatic process where the heat exchanged by the system is zero. So as I defined earlier, dq is equal to summation En dPn. So in order to dq to be zero, dPn should be zero. That is, the occupation probabilities should remain constant. So there's a slight difference with the classical adiabatic process. So the classical adiabatic processes are fast enough. So the occupation probabilities in classical adiabatic process need not remain constant. However, for quantum adiabatic processes, which we consider to be slow enough, that the population distribution remain unchanged. So in this table, I have summarized all the invariant quantities in classical and quantum thermodynamic processes. Like for classical isothermal process, the internal energy and temperature are invariant quantities. For quantum isothermal, temperature is the only invariant quantity. Similarly, you can see for isochoric process, En is the invariant quantity, that is energy eigenvalue. And for classical isochoric process, the volume, because the work is defined in classically as PdV, so volume remains constant. Similarly for adiabatic processes. So now let's come to types of operational phases. So based on the signs of the heat absorbed or released and the work done by the cycle, they can be categorized into operational phases. So our convention is, if heat is absorbed by the system, so we consider it to be positive, and if heat is given out by the system, so the heat is considered to be negative. And if work is done by the system, work is positive, and if work is done on the system, the work is negative. So based on that, if heat is absorbed by the system, Qin is positive, and if Q out is negative. And if the work is done by the system, that is W is greater than 0, the system behaves as a heat engine. Similarly, if other way around, so it behaves as a refrigerator. And for Joule pump, if both Q in and Q out are negative, and even work is done on the system, we get a Joule pump. And again, if Q in is positive, Q out is negative, and work is done on the system, it behaves as a cold pump. So these are the famous two thermodynamic cycles, as we know, are Carnot cycle and Otto cycle. So these are their quantum versions. So the first figure is quantum Carnot cycle, which consists of quantum isothermal strokes and quantum adiabatic strokes. So A to B, you can see that the entropy remains constant. So that is a adiabatic stroke. And B to C, you can see that the temperature remains constant, and that is a isothermal stroke. And B to C, the system also absorbs heat from the heat bath. So that is Qn. And similarly, C to D is adiabatic, and D to A is isothermal process. Similarly, for quantum Otto cycle, we have isochoric and adiabatic strokes. So again, A to B is adiabatic stroke, and B to C is isochoric stroke. Similarly, C to D is again adiabatic, and D to A is isochoric. So now let's have a sneak peek into our current work. So as I told you, for quantum processes, we need a quantum working model. So what we did is we chose infinite square well with Dirac delta impurity potential as our working model. We calculated its energy eigenvalues and also plotted them numerically and varied few parameters of our working model to get the following work output density plots. These two of them are for quantum Otto cycle. So in the first figure, you can see that I have varied the position of the Dirac delta impurity and along with the length of infinite square well. And the notable achievement is we could get both. The system behaves as both as cold pump and as heat engine. For some parts of for some values of P, it works as cold pump, and for some parts it behaves as heat engine. Similarly, in the second figure, along with the position of the impurity, we have varied the temperature of the hot reservoir. So in that also, we were able to achieve two operational phases, heat engine and cold pump, with a significant amount of work in milli-electron volt. So indeed, quantum thermodynamics is a young and growing field. So these are some recent advancements in the field, and these it has applications in nanotechnology, quantum many-body information dynamics, quantum dot heat engines, etc. So with this, I would like to stop my talk. Thank you so much.
Thanks, Ritesh. If there are any questions on this talk or on any other of the talks, please feel free to ask. Anyway, thank you so much, everyone. This was a good 1.5 hours spent learning about what others are doing in our group, learning also how to give better talks, and hopefully I'll be putting it on YouTube so that anyone who is interested in learning more about our group can watch this and learn from that. So thank you, everyone. I'm now closing this session.
Thank you, sir.